Hello students, how are you all? Hope all of you are safe and sound at home. Today I am back again to explain few more topics from the chapter Force and Laws of Motion. Today I am going to explain inertia and mass. From my last video we know that inertia of a body is the tendency of a body to remain in its state of rest or of motion until and unless some external forces are applied to change that state. Simply put, a body at rest will continue to be at rest and a body in motion will continue to be in motion. Inertia of a body is also measured by the magnitude of force required to change the state of the body. That means whatever force I require to change the state of a body, that means the state from rest to motion or from motion to rest, is also considered to be inertia. The force required to change the state of a heavier body is more than the force required to change the state of a lighter body. This is because the mass of the heavier body is more than the mass of the lighter body. So, a body of more mass will have more inertia. That means it will try more to be in its state of rest or of motion. That is why we can say that the mass of a body is the measure of its inertia. Now we are going to learn about momentum. Momentum of a body is the product of its mass and velocity. Momentum is denoted by P. So, P equal to m into v, where m is the mass of the body and v is the velocity. The SI unit of mass is kg and that of velocity is meter per second. So, the unit of momentum becomes kg into meter per second or kg meter per second. So we can say that the momentum of a body depends on mass as well as the velocity of the body. If a body is at rest, its velocity is also zero, so its momentum will also be zero. Let us move on to our next topic, that is Newton's second law of motion. It states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. This law provides us with an equation relating force, mass and acceleration. Let us see how. In order to get to that relation, let us take a moving body of mass m whose velocity changes from u to v in time t. So, initial velocity becomes u and final velocity becomes v. We know that momentum is the product of mass and velocity. So, the initial momentum of the body is mu and the final momentum of the body is mv. In order to find change in momentum, we need to subtract initial momentum from final momentum. That gives us mv minus mu. Rate of change of momentum. Here we need to divide the change in momentum by time. So we get mv minus mu divided by t. According to Newton's second law, force is directly proportional to the rate of change of momentum. So, we get F proportional to mv minus mu by t. Here, force is denoted by F and we have already found out that mv minus mu by t is the rate of change of momentum. As we move on to the next line, we can take m common, which gives us F proportional to m into v minus u by t. In place of v minus u by t, we can write ma. A means acceleration, and we all know that A equal to V minus U by T. So we get F proportional to M into A. Here, in order to remove the proportionality sign, we need to put a proportionality constant. Here K is taken as proportionality constant. So F equal to K into M into A. Now if I take the value of F to be 1, so it will produce an acceleration of 1 meter per second square in a body of mass 1 kg. So if I take F to be 1 Newton, then mass will be 1 kg and acceleration will be 1 meter per second square. If I put all these values in equation 2, I get the value of K to be 1. So we can write F equal to ma. This is how we get to the relation between force, mass and acceleration. From this equation, we can also say that Newton's second law can be modified as follows. The product of mass and acceleration is the force acting on an object. Now, let us move on to Newton's third law of motion. It states that to every action there is an equal and opposite reaction, and they act on different bodies. That means whenever there is an action and reaction involved, two bodies are required, and action and reaction will always work on different bodies in different directions as well. In order to prove this, we'll do a simple experiment. We'll take two spring balances A and B as shown in the figure and tie them together. We'll put one end of B to a rigid support on a wall, and we'll start pulling another end of A as shown in the figure. We'll see both A and B will show same reading. This shows that force exerted by the spring balance A on B is equal but in opposite direction to the force exerted by spring balance B on A. The force exerted by spring balance A on B is action, and the force exerted by spring balance B on A is reaction. Let us see a few more examples. Whenever a gun is fired, the gun moves in the backward direction. The moving out of the bullet in the forward direction is the action, and the moving backward of the gun, that is what we call a recoil, is the reaction. You can see in the picture given here. If you are in a boat and you jump towards the shore from the boat will tend to move in the backward direction. This is also an example of action and reaction. So we have reached an end to today's discussion. Hope this video will help you in understanding the explained topics. Until next week, take care, stay safe and study hard.